Welcome. So it is my very pleasure to be able to introduce George Davey Smith, our first keynote speaker. So George Davey Smith, who is the director of the MRC Integrative Epidemiology Unit at the University of Bristol, has had a diverse career in epidemiology spanning over 30 years. He has made major contributions to both social and clinical epidemiology, being highly cited in both areas. He has also published widely on various aspects of the history of medicine. You may wonder then why we invited George to be keynote speaker in a Biology of Genomes meeting. There are at least two very good reasons for that. The first one is methodological. Over the last 15 years, George has been instrumental in pioneering the essential method of Mendelian randomization, now a widely used approach for strengthening causal inference, which he continues to develop and refine. Mendelian randomization is rightfully associated with his name. The second is with regards to his early role in the establishment of large, deeply phenotyped population-based cohorts. George inherited ALSPAC from Jane Golding in 2005, and he got GWAS and other omics approaches underway in this cohort and pushed very much for broader and continuous phenotyping. The investment and subsequent output escalated dramatically after he took over. George was instrumental in establishing ALSPAC as one of the most accessible cohorts in the world, with over 1,000 researchers using the data. He is very unusual as a cohort PI in being author on less than 10% of the papers, which is certainly a reflection of his intellectual generosity. George's career has been punctuated by somewhat colorful, maverick tendencies and political persuasion. As an example, George spent time in Nicaragua supporting the Sandinista revolution under cover of the only large-scale randomized control trial of condom promotion for AIDS prevention, which involved a collection of thousands of used condoms in Nicaraguan motels. This led to a publication in The Lancet. He's also certainly the only academic who caused the Tory party to request that the editor of the British Medical Journal be sacked for publishing one of George's papers. We're very grateful that he accepted our invitation and look forward to an exciting talk.
So thank you very much indeed to the organisers for the invitation, although I noticed that you and Bernie has left before the embarrassment of having suggested me as the speaker in this event. And I am indeed an epidemiologist, and so, I don't know if my slides will come on. I am going to talk about Mendelian randomization largely, as mentioned in the extremely generous introduction. As an epidemiologist, obviously we are interested in population health, and in some ways the transformation of population health is becoming a problem because of the huge success that there's been across the 20th century. This is life expectancy trends in England and Wales. These are real trends, and then these are projected trends. But just since 1981, with about a quarter of a year life expectancy added per year, extraordinary advance. And this, of course, went on across the whole of the 20th century from a life expectancy of less than 40 at the turn of the 20th century. And clearly the major drivers of that transformation in life expectancy have been changes in the environment, in the social, physical environment, which have led to this transformation. And of course, now with pension costs, etc., the projected life expectancies now indeed becomes a political problem. But I guess then the question comes, why, as an epidemiologist whose entire interest is in modifiable processes that influence disease, so my interest is in identifying factors that you can change, and through changing them you actually influence disease initiation or progression. Why should one be interested in genes being things which are, of course, fixed largely at conception? And so I guess the best answer to this question is this advert in the Boston Globe sent to me by my friend Nancy Krieger. The average American lifespan has increased nearly 3 years over the last 2 decades. We've been selling vitamins at a discount since 1977. Coincidence? We don't think so. And I think vitaminshop.com may have got a pecuniary interest in you believing their advert. But the reason that they could publish such adverts is because of epidemiological studies which demonstrated that observationally taking vitamins was indeed associated with lower risk of coronary heart disease. This is one huge study from Boston, the Health Professionals Follow-Up Study, where the participants were asked if they were taking vitamin E supplements, and then they were followed up. All the other risk factors were measured. All of the other risk factors were adjusted for in the way that one can do in those models. And there appeared to be a 40% reduced risk of coronary heart disease amongst the people who were taking vitamin E supplements, which appeared even after 2 years. So short-term vitamin E supplement use appeared to lower the risk of vitamin E. And this was reported in the New York Times as vitamin E greatly reduces risk of heart disease, studies suggest. There was a companion study from the Nurses' Health Study showing the same thing in the same issue of the New England Journal of Medicine. You know, the point, so a causal claim really is made here that vitamin E, that taking vitamin E will reduce your risk of heart disease. You'll probably be unsurprised to know that when large-scale randomized trials, there's over 60 of them now with up to 13 years of follow-up, of randomizing people to either vitamin E supplements or to placebos, when they appeared, they had absolutely no effect on coronary heart disease. So here you have a situation where the observational studies are measuring precisely the same thing as the trials, taking vitamin E supplements. There's no issue about you not studying the same thing in the trials and the observational studies. You're studying exactly the same thing, but confounding, because vitamin E supplement use is associated with so many other factors, simply cannot be controlled for statistically. One cannot adjust for it. And other biases exist in these studies, which is sort of disheartening for epidemiologists. So much for the antioxidants. As you head to heaven, you still go to heaven or to hell, eventually independent of whether you take them, but they don't shorten the time anyway. And maybe so much for observational epidemiology. This is a cartoon, you know, the random medical news from the New England Journal of Panic-Inducing Gobbledygook. So the newsreader just presses the button and the wheels spin round. And today's story is that coffee causes depression in twins. That's today's association. And of course, all of these associations are spurious, except red wine does cause sexual dysfunction in men aged 25 to 40. Although sadly, I can only now talk from the long ago memories of such things. So this is how I became interested in the use of genetic variants as what in observational studies, especially in econometrics, are referred to as instrumental variables, which are factors that you can use as pseudo-randomizers, as ways of producing data equivalent to that produced in randomized controlled studies, or at least getting closer to that. Because in genetic association studies, the laws of the Mendelian genetics would imply that if you define groups by the carriage of particular genotypes, then those groups will differ only with respect to the locus under study and closely related loci and linkage disequilibrium. And also that those genotypes will not be associated with social, behavioral, physiological factors in the same way that if you measure behaviors or phenotypes, circulating biomarkers or whatever, they are strongly influenced by and associated with those confounding factors. And also importantly, disease processes will not influence your germline genome. Whereas disease processes will influence both behaviors, but also will introduce physiological markers and biomarkers. And so when one is trying to determine whether factors are causally related to disease, if biomarkers are causally related to disease, one can be misled because you're actually looking at something where the biomarker has been influenced by very early stages of the disease process. So the principle of Mendelian randomization is that if you have a germline genetic variant which is related to an exposure, then that will not relate to these underlying confounding factors that associate to both your exposure and your outcome, nor can the outcome itself influence your germline genome. So you're interested, obviously, in the association between exposure and outcome, and you measure that in your observational epidemiological study. But but to take one example, this is a C-reactive protein, which is an acute phase reactant, which is a strong predictor of coronary heart disease. This association exists, and adjusting for confounders, just like with vitamin E, it doesn't remove the effect. Early stages of coronary heart disease, atheroma is an inflammatory process, and early stages of coronary heart disease influence acute phase reactants like C-reactive protein. People try to take that into account by excluding the first 10 years of follow-up or 5 years of follow-up in observational studies, but one cannot completely exclude the effect of reverse causation. But of course, reverse causation will not occur between coronary heart disease and germline genotype. So if you have a genetic variant related to, in the CRP promoter region is the one that is used in these studies, related to CRP levels, then if CRP causally increased the risk of coronary heart disease, the genetic variant associated with higher CRP should also be related to coronary heart disease risk. And the genetic variant will not be confounded by these sorts of factors which confound observational epidemiological studies. So you study that, you analyze the genotype against outcome, and that gives you an estimate of the causal effect of your exposure on your outcome. Or in the parlance of instrumental variables analysis, you have your modifiable exposure, C-reactive protein, you relate it to your outcome, but there's both confounding and reverse causation. It's often impossible to exclude these with observational data. You have an instrumental variable here, the genetic variant. It relates to the modifiable exposure, your C-reactive protein. It is not associated with confounders. There's no reverse causation. And the association of the instrumental variable with coronary heart disease, and then applying the mathematics of instrumental variable analysis, allows you to get an effect estimate with precision estimation of the causal effect of your modifiable exposure, C-reactive protein in this case, on your outcome. So just a couple of examples before I talk more generally about limitations and expansions of this approach. Here's 3 biomarkers. I've talked about C-reactive protein. 2 others, there's interleukin-6 and fibrinogen. These are all acute phase reactants. They all respond to things like inflammation, infection, etc. They all strongly interrelate. This is C-reactive protein level against interleukin-6 level. I mean, interleukin-6, if you infuse people with it, increases their CRP. CRP is driven by it, which is partly why there's this strong association. Interleukin-6 and fibrinogen associate. Fibrinogen is a clotting factor related to blood clotting. And C-reactive protein and, interleukin-6 and fibrinogen and C-reactive protein and fibrinogen interrelate. These 3 factors strongly interrelate, and statistically you simply can't separate them. They all predict coronary heart disease. The reason why interleukin-6 has a less clear pattern is probably because there's a much smaller number of events available in those studies because it's expensive to measure. Now, if you take the genetic variant in the promoter region of CRP gene, which is associated with a big difference in C-reactive protein, well, relatively big, about 1 to 2%, 1% of the variance, but big for these common genetic variants. About the same, in fact, as the effect of blood pressure lowering tablet on the variance of blood pressure. It's about what explains about 1% of the variance in a trial where you give 50% of people blood pressure lowering tablet and 50% of placebo. So it's like about the same effect as something you could randomize. But the genetic variant is not associated with this. There's a large number of confounding factors. We actually looked in a different study at 120 confounding factors, and you got no more associations with physiological factors, socioeconomic factors, etc., than you would expect by chance. So it relates to a very robust difference in C-reactive protein level, but is not associated with confounding factors. There's four variants in that gene which are associated with CRP. They do not associate with coronary heart disease in a robust way. In the observational data, you get a strong effect of C-reactive protein when you measure C-reactive protein itself on coronary heart disease, which is attenuated but remains highly statistically robust and above 1 on adjustment for all the confounding factors that we saw in that list and others. And yet, when you look at the genotype and you do an instrumental variable analysis to predict using the genotype to give you an estimate of the causal effect of C-reactive protein on coronary heart disease, there's no effect at all. And for fibrinogen, there is also, using Mendelian randomization, no evidence of a causal influence of fibrinogen. But for interleukin-6, the suggestion is, from 2 large-scale Mendelian randomization studies, that higher interleukin-6 level is indeed related to, or activity, is indeed related to higher risk of coronary heart disease. And there's an ongoing trial, the ENTRACT trial, which of IL-6 receptor blockade to see if this reduces risk of coronary heart disease. In this case, the Mendelian randomization studies would predict that there should be a beneficial effect. So Mendelian randomization, as well as being seen as an instrumental variable approach, can be considered as analogous to a randomized controlled trial. In a randomized controlled trial, you randomly assign people to placebo or to treatment, and I'm going to use the example of selenium, a real example of selenium supplementation. This is in a trial called the SELECT trial, where men were given selenium in an attempt to prevent prostate cancer. And plasma selenium is, of course, increased in the group that you randomize to the selenium supplement as against the placebo group. But the randomization ensures there's no confounding factors that differ between the groups. And also, of course, the outcomes can't influence what you are retrospectively randomized to. So there's no reverse causation. And so Mendelian randomization, the randomization is by meiosis, but you end up with 2 groups that you can separate by genotype, which do not differ in confounding factors, for which there's no reverse causation. And with a genetic variant, this is a real genetic variant related to a difference in selenium of about 0.5 micromoles per liter, so it's about a third of the effect that was produced by the randomization in the trial. And in the randomized controlled trial, the outcome was essentially null. Relative risk was 1.04 with confidence intervals 0.87 to 1.24. This was in the SELECT trial. And then in a Mendelian randomization analysis, which Richard Martin and colleagues carried out in a very large prostate cancer consortium, genetic consortium, the practical consortium with 22,000 cases and 22,000 controls, the relative risk for the same 1.27 millimoles per litre, you scale it in your instrumental variable analysis. It's all fairly trivial. Doing these analyses with confidence intervals 0.9 to 1.22, very similar to that seen in the randomized controlled trial. But this is just to get over the analogy between the two and the fact that you can utilize the two to get estimates and then, of course, compare them. An exciting potential development with Mendelian randomization is the introduction of what are called 2-sample instrumental variable methods into the Mendelian randomization armory. 2-sample methods are ones where your genetic variant and your intermediate phenotype of interest, so your selenium level or your C-reactive protein or whatever, that can be gathered from one very large study. And then if you have very large case control studies that have not measured that factor but come from populations which carry the same variants and where you know, at least in subsamples, that the variants relate in the same way to the intermediate phenotypes, you can then utilize the data from the 2 samples to calculate a predicted causal effect, which allows one to use the very large-scale GWAS case control samples available through consortia and the coming very large-scale GWAS population studies, such as the Kadoorie Biobank in China, UK Biobank, of which I'm a participant in the UK. When the GWAS data become available from those studies, you'll be able to apply these methods, these 2-sample methods, using data from those studies and then applying them to outcome studies, even for rare outcomes like where you've had to gather them through case control studies. And that And here's an example of a two-sample Mendelian randomization study carried out by Philip Haycock and Richard Martin in the ILCO consortium. This is a lung cancer consortium that we work with 11,000 cases and 26,000 controls. And firstly, looking at body mass index, the observational estimate, I'm not sure if people are aware of this, the observational estimate shows very strong protection of higher body mass index against lung cancer in prospective studies, even when the body mass index is measured 30 years before. This even led the World Cancer Research Fund suggested that low body fatness is classified as a possible cause of lung cancer because this is such a well-replicated finding. But of course, smoking is confounded with many other factors, and smoking reduces body mass index. Mendelian randomization shows, along with other evidence, that smoking leads to reduced BMI. So you have the causal factor is also influencing your exposure. So there's very strong confounding, and using the genetic variants related to body mass index, your predicted causal effect is certainly not protective. And you can show this that you can do a heterogeneity statistic suggest that these are different estimates. So the observational effect suggesting higher BMI as protective of lung cancer is not seen in the Mendelian randomization study, and in my view is more plausible. And for C-reactive protein, the observational estimate is strongly positive, just like with coronary heart disease. C-reactive protein is a strong predictor, it's a predictor of lung cancer risk, but the causal genetic estimate is null. But this is just examples of where of course, you don't have CRP level measured in ILCO. It's a case control study. You don't have the prospective measures anyway in most of the component studies within it, but you don't need that to carry out two-sample MR assessments. And here's a similar one of a whole host of metabolites in cardiogram, big coronary heart disease case control study. You're not meant to be able to read these. This is just showing how you can test a whole load of genetic variants related to the very large number of metabolites for which there are now robust genetic indicators. But just one thing to notice is that some of these they're just X12844. That's because the company which generates this mass spectrometry metabolomic data knows there's some peaks, but for some of these they have not identified precisely what the molecule is, and they don't, but they tell you that this peak exists in your this factor exists in your data, it's quantifiable, and then you can do GWAS of that, come up with genetic variants related to that, and then suggest that this unknown factor is then related to disease, and that then would mean it would be worth your while doing the expensive chemistry for finding out what this is. So you can actually screen metabolites that are unknown. There's 6,000 lipid metabolites, many of which it's actually unknown exactly what their chemical composition is in which they are. But if the genetic evidence suggests they may be causally related to disease, it's worth interrogating the chemistry further. I'm going to talk about now multiphenotype Mendelian randomization, because when talking about the metabolites and the lipidomics, of course, these factors all very strongly intercorrelate. And one, a very simple, in a way, example of multiphenotype exploration in epidemiology is the investigation of low-density lipoprotein cholesterol, high-density lipoprotein cholesterol, or so-called good cholesterol, and triglycerides in their association with coronary heart disease. And this is the latest large-scale meta-analysis, systematic review from the Emerging Risk Factors Collaboration of these three lipids. And I'm just going to focus on triglyceride level and HDL cholesterol level. Triglycerides in this huge collaboration is positively associated prospectively with coronary heart disease risk. But when you adjust for confounders, in particular HDL cholesterol, that attenuates pretty much to the null, which is what most studies show. Whereas HDL cholesterol, or so-called good cholesterol, the higher the level, the lower the risk of coronary heart disease. And whilst adjustment does attenuate this effect, the effect remains statistically robust. And these sorts of analyses have led the focus to be on HDL cholesterol, because this is seen to be the factor which shows the best epidemiological evidence. And the authors of this 2009 JAMA paper conclude the current findings suggest that therapy directed at HDL cholesterol as well as non-HDL cholesterol may generate substantial additional benefit. So they are suggesting that targeting HDL cholesterol, lowering HDL cholesterol, may produce benefit on the basis of their observational data. Now, 25 years ago, myself and my colleague Andy Phillips, a statistician called Andy Phillips, looked at this issue of triglycerides and HDL cholesterol. And we utilized data from the British Regional Heart Study. And we were concerned that we think that these two factors so strongly intercorrelated, given the inevitable measurement error, the fact that you're not absolutely certain which component of for example, one's day-to-day variation in them might be important. Triglycerides increase dramatically after a high-fat meal. Maybe it's postprandial triglycerides that are important, not fasting triglycerides, which are usually measured in studies. So we did the standard analysis, like was done 20 years later by the Emerging Risk Factors Collaboration, where you adjust one for the other. And like most people showed, we showed that the triglyceride effect attenuates quite considerably. The HDL cholesterol effect attenuates much less. We just flip that so that they're on the same scale. They both point up, but the HDL cholesterol is protective. We then did a whole series of simulations of simulating different degrees of measurement error in triglycerides and HDL cholesterol. As I say, triglycerides vary dramatically postprandially after eating. But so we simulated the data if the triglyceride interclass correlation was 0.7 and HDL intraclass correlation, i.e. just taking two measurements at random, and the correlation across the two measures was 0.9. And then, of course, once you take the measurement error into account, the effect estimates increase for both triglycerides more than HDL cholesterol because you've got more measurement error in the simulation. But then the mutual adjustment still demonstrated a greater effect for HDL cholesterol. But if we change that to 0.6 and 0.9, the situation flipped. So once you take these levels of measurement error into account, the triglyceride effect, of course, increases on correcting for measurement error, but is less affected by adjustment for HDL cholesterol in this situation, and is seen to be the stronger factor. And then if you just change it from 0.6 to 0.9 to 0.6 to 0.95, it flips back again. So this led us to conclude that trying to get reliable evidence from the observational data in these levels of high correlation was simply not possible. And I actually stopped doing this type of epidemiology and went off to do useful things like randomizing condom in Nicaragua and childhood diarrheal work and developing methods in meta-analysis and stuff like that, because I sort of thought, when you look at this and you sort of think, how would this apply to the data I'm looking at now? You think one's not getting reliable results. So that's like I have to declare I have a vested interest in the outcome of the triglycerides HDL cholesterol story. But now there's some lovely work that's been done with the genetic variants, around 150 genetic variants related to lipids by Doe et al., Seka Kathiresan, as the leading this work, where they looked at all the variants related to LDL cholesterol, and then because these variants have effects on the other lipids as well, they took that into account by adjusting for the effects of all the SNPs on HDL cholesterol and triglyceride, and then on both. But for the LDL cholesterol SNPs, you see that the effects remained robust, whereas for the HDL cholesterol SNPs, taking into account the effect of the SNPs on the other lipids, led to attenuation to the near null. So flip it just so that you can compare them together. For the triglyceride SNPs, this looked rather more like the LDL cholesterol story. There was rather little attenuation on adjustment. But of course, the problem is you are still adjusting for a phenotype, but you're adjusting for an on-average phenotype at a group level, which does not have the same characteristics, measurement error characteristics, and disturbing your analyses as it would in individual level data. But it's still problematic. But this definitely leads to a different conclusion than we saw from the 2009 observational collaboration, which thought that HDL cholesterol looked like a target. On the basis of the genetic data, one would think rather less that was the case. And as I'm sure, as most of you know, there's been a whole series of trials with different classes of drugs which influence HDL cholesterol through different routes, through different mechanisms. But all of them, all of the drugs which have influenced HDL cholesterol and have not had a large influence on other lipids, they've generated big differences in HDL cholesterol. This is the effect on HDL cholesterol, but no effect at all, or adverse effects possibly off target in one of the trials on coronary heart disease. I think the genetic evidence here would have pointed in a different direction. Now, the limitations of Mendelian randomization, obviously the major one is the potential for reintroduced confounding through pleiotropy. I think it's important, though, to consider what one is talking about when talking about this limitation of Mendelian randomization. However, you can consider two broad categories of pleiotropy. One would be pleiotropy where there are downstream effects of an initial phenotypic influence, which was referred to by Grunenberg, who was one of the people really to develop the concept of pleiotropy after Plate in 1910. Grunenberg referred to this as spurious pleiotropy because he didn't see this as being genuinely pleiotropy. It was you influence one phenotype and that had downstream effects on other phenotypes. Or relational vertical type 2 or mediated. These are all terms that have been used for this. The terminology is confusing. As opposed to genuine mosaic horizontal type 1 or biological pleiotropy where a single variant or single variation is generating two phenotypic effects, independent phenotypic effects, and those those might influence your outcome. The type 2 pleiotropy, mediated or spurious, is not only is it not a problem for Mendelian randomization, it is the very essence of Mendelian randomization that you're using a genetic variant which influences one factor, and then you're using that to learn about downstream factors which are influenced by that initial phenotype. So this form of pleiotropy, which Wagner and colleagues, I'm sure you know there's a rather heated debate about this, but Wagner and colleagues suggest is by far the commoner the type at genome-wide scale, is not an issue. The issue for Mendelian randomization is when there is a horizontal pleiotropy. So this can be interrogated in various ways. One is to use multiple genetic variants, where it is simply not plausible that the different variants would have perfectly balanced pleiotropic effects that scale perfectly with their effects on the phenotype of interest. This is a series of 9 SNPs from 6 genes that influence LDL cholesterol. This is on the x-axis is the extent to which the variants relate to LDL cholesterol, and the y-axis is the proportional risk reduction for coronary heart disease. PCSK9, relatively rare variant, has a big effect on cholesterol and a big effect on coronary heart disease. And then these variants, like LDL receptor variant, common variant, has a smaller effect on cholesterol and a smaller effect on coronary heart disease. And what you see, of course, is that these scale beautifully, that the effect of the variant on cholesterol is mimicked by its effect or reflected in its effect on coronary heart disease. For these data to be generated by pleiotropic effects, there would have to be perfectly balancing pleiotropy for all these different genes on different chromosomes working through different mechanisms, which becomes decreasingly plausible as you have more and more genetic variants. A second method is you can adapt methods of bias testing for meta-analysis of randomized controlled trials. Funnel plots and Egger regression, which are used to detect small study bias. And this is in press, and it might be, if it's confusing to people who have not maybe worked in meta-analysis, the paper will be out in a couple of weeks. But this utilizes a test we developed 20 years ago within meta-analysis. The first thing one did was look at what's called funnel plots, which is where you plot the precision of your effect estimate against your outcome. This is your odds ratio. And the point is, in trials, in randomized controlled trials, small trials which were generating just by chance were getting large effects would get published, whereas small trials that weren't generating such effects would stay in someone's file drawer and not get published. So a whole series of methods were developed to see is there evidence of what's called small study bias, where the smaller studies are generating different results from the larger studies, which is what you'd expect to see in this situation. And this is for beta blockers in myocardial infarction, where you see what you should see, which is a balanced funnel. If the negative trials were missing, you wouldn't see these negative trials wouldn't appear. You would just see the positive trials. So you'd see an unbalanced funnel. That's what a balanced funnel looks like for something which works. Beta blockers are useful in myocardial infarction. This is a famously biased or asymmetrical funnel where lots of small trials showing implausibly huge reductions in coronary heart disease, trials of 100 and 200 people, of injecting people with magnesium after heart attacks, suggested there was high benefit. One slightly larger trial appeared, and an ethics committee was urged not to approve a larger trial because it was so obvious that this stuff worked. But then when the very large-scale ISIS trial appeared, there's absolutely no beneficial effect. Now, in the Mendelian randomization context, one does, and the regression test is a regression of this effect. You can do the same thing, because if you consider that genetic variants are associated, that have smaller associations with your phenotype of interest, i.e. LDL cholesterol, if the pleiotropic effects exist, then the pleiotropic effects could push those in both directions. And the pleiotropic effects would more likely win out when the actual effect on your phenotype of interest is smaller, and therefore your effect on your outcome through your phenotype of interest is smaller. And this is what the whole 150 variants related to LDL cholesterol look like. Just perfect. The bigger the effect on cholesterol, the bigger the effect on coronary heart disease, and just a perfectly balanced funnel. No suggestion of one losing, there being missing effects. And if you actually selected the variants related to LDL cholesterol by the ones which didn't have any effect on any of the lipids with an arbitrary p-value cutoff of like 0.05, as various people have done, you actually generate a biased, a subsample which looks more biased. And then you can do this, and then you can carry out the Egger regression, whereby you regress the effect of the SNP on cholesterol against the effects of on coronary heart disease. And you'd expect the bigger the effect on cholesterol, this is lower cholesterol, the bigger effect on lower coronary heart disease, as I showed in the plot, just with a few of the variants. And then if you do not constrain your regression to run through 0, the intercept gives you an estimate of the overall pleiotropic effect, pushing for the whole 150 variants combined, the aggregate pleiotropic effect that pushes this away from 0. And the slope gives you an estimate of the causal effect of cholesterol and coronary heart disease. So in this situation, even if your instruments are invalid, even if pleiotropy exists and you have invalid instruments, this will both give you a test of the existence of such overall directional pleiotropy, and allow you to have an estimate. And here we have the estimate for just a standard instrumental variable estimate. This should actually be minus 41, 10 to the minus 41 when it's just a standard instrumental variable estimate. This is the Egger regression, which gives a very similar estimate, but there is some evidence of overall pleiotropy. So you lose statistical power by doing this, using this regression method rather than a conventional IV, but your estimates are protected from directional pleiotropy. And in fact, you're doing the subset chosen by there not being an effect on the other two lipids, you actually get a less good estimate. So I'll suggest this here. And of course, if you select a subset, you can always change your cutoff to p of 0.05 to 0.1 or 0.01 or whatever. In this situation where you just use all the variants, but then actually test for the overall effect of pleiotropy, you don't have the problem of you actually selecting your data to fit the answer. And these are just proof of principle examples. Given time, I'm just going to miss these out essentially. But these are just proof of principle examples of a whole host of uric acid SNPs on gout. If you didn't see a causal effect on uric acid on gout, you would give up and do something else. You get very strong evidence of an effect of uric acid on gout. If you exclude the two SNPs with the biggest effect, you still get the effect. But there's evidence of pleiotropic effect, as people who've worked with uric acid SNPs related to uric acid will know that the GCKR is one of those SNPs, the variant which relates to everything you know. So if you do the the IV estimate, the conventional IV estimates are larger and have tighter confidence intervals, but the Egger regression estimates still suggest a very strong causal effect of uric acid on gout, and they suggest that there is overall pleiotropy. So these are estimates. They suggest that the crude IV estimates are influenced by pleiotropy, which does not exist for the Egger regression estimates. And I'll skip coronary heart disease. But a final method I'll mention in my last few minutes is you can interact your instrument with a second exogenous variable. This is a way of testing for instrument validity. And I'll just do this through an example of alcohol intake and the incidence of disease. Alcohol is difficult to study because people misreport alcohol intake. This guy is ticking the one glass a day on your questionnaire about how much he drinks. There's strong reverse causation because whatever you're ill with, if you go to your doctor tells you to drink less. So disease influences your alcohol intake. And also alcohol intake is obviously confounded with a whole host of social, behavioral, physiological factors. This was a news story from the same study that brought us vitamin E supplements are good for you. This was got high blood pressure, have a drink or two. Well, I actually do have high blood pressure, and I quite like a drink or two, so I thought this sounds like good news. But is it true? So you can study this through a Mendelian randomization approach by looking at the metabolism of alcohol in cartoon form. When you drink ethanol, alcohol dehydrogenases convert this to acetaldehyde, which gives one the unpleasant aspects of drinking. So you get palpitations, you get flushing, you get headache, you get guilt. Actually, not guilt, but you get the other adverse effects of alcohol intake. And in East Asian populations, a large number of people carry knockouts of the acetaldehyde dehydrogenase variant, which clears acetaldehyde. And the people who are homozygous knockouts, it's very difficult to find anyone who drinks amongst that group, as these data from a meta-analysis from a lot of years ago now that we did shows. This is amongst men and amongst women. Amongst men, the homozygous knockouts drink very little. The heterozygotes drink an intermediate amount, and the homozygous wild types drink most. Amongst women in these populations, however, at the time these studies were done, women were not drinking whatever their genotype. So this is a lovely case of where you can use an interaction to test your instrumental variable assumptions, because if the genetic variant was having a pleiotropic effect on blood pressure, and it was just through the genetic variant effect, it wasn't anything to do with alcohol, then you would see the effect of the genetic variant in men and women. Because it's a gene, it's in the men and the women, it's having the effect. If, however, alcohol is the causal factor and the gene is having the influence on blood pressure through alcohol intake, then you would only see the effect of men, and you only see it in men. We've now replicated this in 80,000 people in the Kadoorie study with Zhengbing Chen, this interaction. And what you see is that, sadly, the men who are the homozygous knockouts and don't drink have the lower blood pressure. It's quite considerably lower blood pressure. Alcohol increases blood pressure and quite substantially, so I carry on taking the ACE inhibitors. So that's a way of testing your instrument strength as well. So I'm going to finish by looking at Mendelian randomization of pharmaceutical targets. There's many examples where intervention development has been discouraged, like CRP, where pharmaceutical companies were developing interventions on CRP, and the Mendelian randomizations. Mendelian randomization studies put a stop to that, and then PCSK9 and the recent monoclonal antibody studies, which show evidence of reduced coronary heart disease in people with monoclonal antibodies, and MPC1L1 and ezetimibe reported at the American Heart Association, the first large-scale trial of reduced coronary heart disease risk with that. So there's examples there. I'll skip this. It's a nice example. I will actually skip the example. Richard Gibbs gave a nice presentation about this, about phospholipase A2 activity, where there's a knockout which influences activity. The knockout isn't related in the study they published in the New England Journal of Medicine to coronary heart disease, although if you actually do an instrumental variable analysis with the data they report, the confidence intervals are extremely wide on the causal effect. But a meta-analysis of East Asian studies had shown that already in 2010, that this was unlikely to benefit coronary heart disease. But trials went ahead, and GSK heart drug misses primary goal. There's now been 3 trials reported, all of them absolutely null from this, that went ahead despite the existing data from the East Asian populations. And these things do have an effect because there's GSK's share price plummeting after that trial was reported. You can interrogate effects of particular targets versus downstream phenotype, e.g. HMG co-reductase or statins. Is it HMG co-reductase, that particular pathway that matters, or do other cholesterol modifying mechanisms have the same effects? And this shows there's your HMG gene. It's just bang on the line. There's no particular effect of the HMG co-reductase modification of cholesterol and coronary heart disease. You get the same effect on coronary heart disease if you're modifying cholesterol through other pathways. So you can learn about whether it's the downstream phenotype or the particular target. You can learn about off-target effects. The one we published in The Lancet was in The Lancet recently was the HMG co-reductase gene and diabetes, where the randomized trials of statins show a very small increase in diabetes risk with statins, and the genetic variant in HMG co-reductase associated with lower cholesterol also associates with higher risk of diabetes to the same degree. Interestingly, some data coming out are being analysed suggesting that maybe it's just cholesterol lowering which influences diabetes. You can predict factorial pharmaceutical effects, and this is a lovely paper just out by Brian Ferentz's group, where they use the genetic variant which ezetimibe relates to, and the HMG variant. They do a factorial Mendelian randomization by putting by using the genetic variants orthogonally, just like in a factorial trial. And of course, both relate to both HMG and the 2 gene scores relate to lower coronary heart disease, and the combined gene score suggests you get doubling of your effect. So basically, this predicts that what was actually seen in the trial, it was just the American Heart Association, that you appear to get additive effects of combining the 2 drugs. You can look at generalizability of treatment responses, because of course, for statins, the bottom line is a large number of treatments do not show heterogeneous effects across large groups of people. For statins, you get exactly the same effect, whether you've had CHD or not, you're diabetic or not, type 1, type 2, your sex, your age, body mass index, your smoking status, whether you're treated hypertensive. This is the effect of the statins in randomized trials. But it's very rare that one would be able, in a situation, to have enough money to do randomized trials in all of these subgroups, in every subgroup. But if you have a genetic variant which mimics the drug effect, you can relatively cheaply genotype the genetic variant in a particular population subgroup you're interested in. And if the drug is not going to have beneficial effects, you'd expect to not see the association with the genetic variant. So I'd like to finish and just thank my 4 people in particular, Jack Bowden, who works on the Egger regression method, Philip Haycock, and Jim Hamani and Richard Martin, who did some of the analyses, the unpublished analyses that I showed. I'd like to thank them very much. And just to say that Mendelian randomization offers a companion approach to precision medicine. This approach is not interested in heterogeneity of effects across groups. We're not interested in gene-specific effects. It's using genes or genetic variants to tell you about effects, treatment effects, which are going to have effects essentially across the board. But it gives one way for which genetic epidemiology could contribute to improve public health. Thanks very much.
Thank you very much. Questions for George? So I have one to start. So not at all being in the field. So I was wondering whether, so of course the method is extremely convincing, but in what proportion of cases where you would like to use Mendelian randomization do you actually find the genetic variants that allow you to apply the methods?
Yeah, so that's a very interesting point. I mean, we published the first paper describing the method in 2003, and we finished it by saying, the problem is limited number of genetic variants. We were particularly interested in vitamin C and coronary heart disease. There's no variant related to vitamin C levels. But of course, since 2003, with the discovery of variants, there's now very robust variants related to vitamin C levels. So you can do studies of vitamin C and disease. So I mean, the issue is, I think, with biomarkers, particularly metabolites, a large proportion of metabolites, have heritability in twin studies, a large proportion of them already have identified genetic variants, even with GWASs, which are small by disease standards. And that's probably because they're sort of more proximal phenotypes. And the same is you can apply Mendelian randomization to, metabolites. You can apply it to, epigenomic markers. Again, where the genetic variant effects, especially the cis effects, are much stronger than you get for downstream phenotypes like body mass index, etc. So, I would be hard pressed to say what proportion, but it's an increasing proportion of factors that one's interested in. There can be genetic proxies for.
Hi, George. Over here.
Hi.
Great talk. As an advocate of MR, as you know, myself, I'm amazed that the community, as sort of papers are coming out and papers get reviewed and reviewers are grumpy, there's actually not widespread consensus about the utility of the approach. There's actually, I think, a bit of criticism about generally adopting it, particularly about the two-stage design. So my question is, what do how, in your view, what would be the way to sort of help really start making really convincing cases so that the community sort of adopts the idea and approach more broadly and sort of advocates it more, sort of rather than sort of be skeptical and resistant to sort of more advocate and diffuse the utility of it?
Yeah, I think there'll be situations where we're actually getting prospective trial data coming out for things where the Mendelian randomization studies are making predictions and what will happen to those predictions. I think there are some cases like the PCSK9 case where the genetic studies came out before the trials. I think the pleiotropy case is the same if you look at the East Asian genetic studies and the ezetimibe, obviously. So I think myself, I get the sense that there is a shift to greater interest in the method. I think after we published the 2003 paper, all that appeared, the citations it got for the first couple of years were people saying this is ridiculous, do something else. I think that my own view is there's a shift. I also think that the methodological developments, and especially the availability of the multiple instruments, which is the really powerful tool, is when you've got large numbers of variants working through different mechanisms, which allows you to make inference about the downstream phenotypes which one wants to influence. I think the multiple genetic variants is also the way that is going to be really important for strengthening the utility and providing convincing examples.
Okay. A beautiful talk. And if we wanted to increase, even more rapidly accelerate the number of variants that you could look at with this sort of method, is there something particularly a direction to achieve that? Certainly it's increasing as we just gain general genetic knowledge, but is there anything proactive?
One thing that quite a lot of people have been playing around with, Dave Evans, and we had a paper in PLOS Genetics last year doing this, and elsewhere, is whether in situations where you haven't got robust genetic variants, but you've got polygenic prediction, can you use polygenic predictors? Now, the thing is, the polygenic predictors, obviously, it's going to be a pleiotropy nightmare. So, it is the problem. And there's a real problem where I said vertical pleiotropy isn't a problem for MR. It's a problem if you don't know what the variants are, because the problem is you might think a variant is a variant for a factor, but it's in fact influencing that through an earlier influence. So, for example, with CRP, when you do Mendelian randomization with CRP, you look through the top hits and the GWAS, and you say FTO's on the top hit. BMI influencing variant because BMI increases your CRP. So you say we're not going to use that. But if you didn't know that, you would be including these variants where they're associated with that from the downstream effects. So the thing that we're working on and other groups are working on is then using the polygenic predictors, but then using these sorts of methods of splitting the polygenic predictor up into randomly and repeating these permutations lots and lots of times and doing these forms of regression analyses where the predictor could be pleiotropic and you'd still be able to get some estimate. But I think with things like Biobank, when you have the 500,000 people and you can generate these predictors within the data, for example, that would be really powerful.
Time for one last question.
So just continuing the theme, thank you for the very clear exposition. Continuing the theme of many instruments, can you see some way to then flip that problem around and start splitting those instruments down into the different mechanistic classes that they occupy? Because that's one of the central problems that we have.
Yeah.
There's an embarrassment of riches
Yeah.
and heterogeneity.
No, I think that's a really good question, and I think that's definitely the way. I know people who work particularly in the lipids field are working on exactly that. I was thinking about how could we combine these to influence the disease through different pathways. The issue is that has to be done prior to use of the instruments, if you like. That clearly that can't be selected on outcome associations. So that those selections need to be on the basis of the knowledge of the pathway which is being influenced. But I think that's definitely the way that, especially for target development, that's definitely the way things are going.
Okay, well, let's thank George for a very interesting talk.